Rigid point cloud registration has always been a foundational yet challenging task in 3D vision and robotics. Given two partial overlap point clouds, the goal is to estimate an optimal rigid transformation to align two 3D point clouds. The major obstacles to point cloud registration come from the large proportion of outliers, low overlap, and the lack of abundant constraints such as texture and color. Recently, many works focus on improving the registration performance of partial overlap point cloud registration. And it has achieved huge success in incorporating transformer into point cloud feature representation. However, as shown in the table, the registration performance of recent transformer-based point cloud registration methods significantly dropped from 3D match to 3D low match. The transformer-based methods usually adopt a self-attention module to learn intra-point cloud features first, then utilizes a cross-attention module to perform feature exchange between input point clouds. The advantage of transformer models mainly benefits from the use of self-attention to capture the global correlations in feature space. However, such global correlations may be ambiguous and lack distinctiveness, especially in indoor low overlap scenarios. Because the correlations with an extensive range of non-overlapping points introduce ambiguity. Our motivation lies in that the low overlap ratio between the 2 point clouds is the key factor that causes feature ambiguity in self-attention. To address this issue, we present PEAL, a prior embedded explicit attention learning model. Our method consists of 3 key modules. First, we utilize existing 2D/3D registration methods to acquire overlap prior. By incorporating prior knowledge into the learning process, the points are divided into 2 parts, anchor points, and non-anchor points. The anchor points include points lying in the putative overlapping region, and the non-anchor points include points lying in the putative non-overlapping region. And the overlap ratio of the anchor region is significantly improved. Then PEAL explicitly learns one-way attention with the putative overlapping points. We perform one-way attention after the standard self-attention. The one-way attention is computed by explicitly learning correlations between non-anchor superpoints and anchor superpoints. Similar to cross-attention, we compute the feature correlation between the non-anchor superpoints attention features and anchor superpoints attention features. We update the non-anchor superpoints attention features for the 2 point clouds, while the anchor attention features of them remain unchanged. The one-way attention module significantly improves the feature distinctiveness and final registration performance. For more details, please refer to our paper. Lastly, during the inference period, we propose an iterative update module, which computes the self-overlap prior based on the currently estimated transformation and then iteratively transfers the prior into the network. To acquire overlap prior, we consider 2 methods. The first one is utilizing the current SOTA point cloud registration methods, and its estimated overlapping regions can serve as a 3D overlap prior. On the other hand, inspired by multimodal learning methods, it is worth considering the use of 2D images in RGBD datasets. Image matching approaches could be utilized to estimate 2D correspondences, which can then be projected onto point clouds through a projection module. By doing so, we can obtain a preliminary estimation of the overlap between images, which serves as a 2D overlap prior. Given the overlap prior, then the points can be divided into 2 parts. We build our methods upon GeoTransformer. We introduce 2 models depending the methods of obtaining prior. Here we show the evaluation results on the 3D match and 3D low match benchmarks. Similar to our baseline method GeoTransformer, we evaluate our method using RANSAC estimator and LGR estimator. As shown in the table, the 2 models of ours both achieve significant improvement in registration recall on both 3D match and 3D low match. Then we show the evolution of the refined pose using an increasing number of iterations. As shown in the figure, the registration recalls of our 2 models continue to improve with increasing iterations. And we also combine our method with another transformer-based point cloud registration method Predator to evaluate its effectiveness. When plugged into Predator, which is not a coarse-to-fine method, the improvement is also prominent. Specifically, the registration recall improves by 10.4% with 2D overlap prior on 5,000 sampled points. At last, We provide some qualitative results with GeoTransformer. For more visualizations, please refer to our paper. Our code and data will be available on GitHub.